The next presentation is by Dr. Ulrich Klotz, who got his degree in physical metal engineering at the Stuttgart University with a PhD in science of materials at the TCHD in Zurich, Switzerland. As director of the Department of Metallurgical Physics and Physical Metallurgy on precious metals and metal chemistry at Schwäbisch in Germany. At FEM. Dr. Klotz will talk about the strategies for the development of new jewelry alloys. What can we learn from other industries? Dr. Klotz will present a study exploring the potential benefits deriving from strategies coming from other industries to improve the development of alloys in the production of jewelry. This interdisciplinary approach aims at accelerating the discovery and the optimization of alloy compositions and to pave the way to sustainable, innovative procedures, providing new ideas for the development of jewelry and watches.
Pleasure to be here again this year, and I welcome you to my talk. I'm going to give an introduction first and then talk about the typical alloy development approaches that are around. Why is alloy development necessary? I will show you some experimental techniques and some simulation-based techniques that can be used for alloy development. And finally, I will go into a point about digitalization in material science, which is a current trend to treat data from different experiments. Now, first, when we want to develop alloys, we have a wide selection of compositions that we can choose from. There are different types. Solid solution-based alloys are the standard alloys that we are using, but there are also other special alloys like intermetallic or amorphous alloys. I will show some examples. And in this first graph, I'll show you just a calculation based on mathematics. If you want to select alloy developments for an alloy, you have to combine them. And you have to map the properties as a function of composition and temperature. And this is usually plotted in a so-called phase diagram. Now, if you have two elements, you can make one binary phase diagram, just one mixture, gold and silver. If you have three elements, gold, silver, and copper, you have one ternary system, but you have gold and silver, you have gold and copper, and you have silver and copper, so you have three ternary systems. Now, if you look at a typical 5-component system, this is I don't know if this is working here. This is something we're using, gold, silver, copper, palladium, zinc, a typical selection of elements that we're using in white gold. We see that we already have to know 10 binary systems, 10 ternary systems, and 5 quaternary systems. So this is a huge space, and we don't know this space. So we only know the regions around one corner, let's say the gold-rich corner, the silver-rich corner, the copper-rich corner, the palladium-rich corner, but you're aware that a gold alloy is very different from a copper alloy and from a palladium alloy. So actually we know very little about the space in between. And so it's actually a no man's land that needs to be explored. And there is a very interesting development going on at the moment, so-called high entropy alloys. This is a special class of alloys where all elements are mixed in a similar range. So 5 elements and every element around 20%. And so this, it was found for steels or other aluminum containing alloys, that such alloys are giving very interesting properties that are different from conventional alloys. So knowing all these systems experimentally is an extremely hard work and very difficult to solve. And therefore, we need some screening approaches, which I will talk about. So let's first start with what we are knowing. We know alloys like these, gold, silver, and copper. We have 75% gold or 58.5% gold for 18 and 14 karat. And we know how the atoms arrange. So we have solid solution-based alloys, and then we have so-called ordering. This means the alloying elements are taking special places, and this gives the hardness in red gold. Now there are other alloys, like these alloys with the pretty colors. They're based on so-called intermetallic phases. They only form at a very special composition where the atoms take a special arrangement. And we know blue gold and purple gold. And we also know these alloys for many technical applications. Titanium aluminides are used in jet engines. Nickel aluminides are also used for high-temperature superalloys, also in jet engines or turbines. We know nitinol, shape memory alloys, that is used in the medical area and for technical purposes. So we also know some intermetallic precious metal-based alloys. And so there is a wide space that is not yet fully explored for alloys that might be used for jewelry applications. Then here is a little movie, the lower image. Maybe you can play this, please. So this is something I presented last year. This is a bulk metallic glass, a platinum-based alloys, which has extremely high elasticity. So you're seeing my colleague Lisa, she's dropping this ball and it bounces back like a rubber ball. And that's because of the very high elasticity of these alloys, and that is very different from conventional alloys. So these alloys form at very special and specific compositions, and therefore it's also important to find out these compositions. And just by melting alloys after alloy, this is very time-consuming and also money-consuming, so we need screening techniques to find such compositions. Now, let's look at where simulation can help us in alloy development. So first of all, for the material properties, to determine them, simulation techniques are very helpful. And also for high throughput calculations to screen whole composition ranges, wide ranges, with many thousands of alloys. I will show some examples for this. So first of all, why do we want to do alloy development? We want to improve the properties like hardness, scratch resistance. We know in many years ago, nickel was replaced by nickel-free white gold alloys. We know about tarnish-resistant silver alloys or red gold alloys with high color stability. And in general, we want to improve the whiteness of the white gold, the hardness of the alloys. So there are many features that we want to improve with the alloys. And we also have new manufacturing techniques like additive manufacturing. So the alloys that we know might probably not fit perfectly to that process because they were developed for casting, they were developed for cast and wrought alloys, so not necessarily they are fitting also to additive manufacturing. And we want to have exclusive companies like special colors. And finally, there are laws or regulations that prohibit special elements, or we have elements that are mined with unfair conditions, and we want to exclude these elements from our processes. So these are all reasons why we want to do alloy development. And if we want to develop alloys, we have to know their properties. There are many properties that the material can have. We have to know this for the production, like our processes. to produce them, but also our process to make sheet, to make wire, and so on. And we also need it as input parameters for simulation. And what parameters are around? We all know the mechanical parameters. They are quite easy to determine: tensile stress, elongation, hardness, reduction of area, and so on. Thermal properties, we are also aware: solidus, liquidus temperature, thermal expansion coefficient, and also those properties are not so complex to determine. But for the simulation tools, we need properties we are maybe not aware of, physical properties: the volume as a function of temperature in the solid and the liquid state, the density, the thermal conductivity, the thermal diffusivity, the viscosity, and also some chemical properties like Gibbs free energies, enthalpy, heat capacity. And these properties are much more difficult to determine with standard laboratory techniques, but simulation techniques can help us to find them if we have a good databases. And this example here shows some properties of standard sterling silver. So the black curve shows the volume fraction of the solid phase. And you see above 900 degrees, the sterling silver is liquid, the solid fraction is 0, and then it suddenly increases during the melting range. And if you look at the green, the red, and the blue curve, you can see that these curves show significant changes during the solidification. The volume is reduced. This is causing the shrinkage problems that we all know during casting. And we see the thermal conductivity increases. This is an important feature for the heat distribution during a casting process, for instance. And we can use these simulation tools to feed our simulation software, like for the casting simulation, for instance, with such parameters. And this is a very important input. Now we can also do the calculation of a solidus and the liquidus range, for instance. And this is an example I prepared for nickel-based alloys. These were alloys with up to 8 components based on nickel. And we wanted to vary the alloy compositions to find alloys with a suitable melting range, with a certain amount of phases. And so I used the high throughput calculation technique and calculated 20,000 alloy compositions. And this plot is showing the results. So you see that the solidus, the liquidus temperature, and the melting range are varying in a quite wide range. And with a set of filters, we narrowed down these 20,000 alloys to about 10 alloys that we found interesting for further characterization. And then we melted these 10 alloys, but we screened a much wider range, and this gives us a much better feeling how the system behaves and what is the role of the different alloying elements. Now, often simulation is not working as good as we would like to because we are lacking of experimental data, because every simulation tool is usually based on experiments. So when we want to make experiments, it's good to also use screening methods, because doing one alloy after the other is a lot of time and a lot of money. But screening techniques are based on samples that show inside the sample there's a certain composition range. And within one sample, we can characterize many alloys without making 20, 50, hundreds of samples. And there are two techniques that I would like to show that are used. One is so-called diffusion couples. We all know colored jewelry with 2 or 3 different colors, like the wedding bands that are shown here. And these rings are usually bonded by diffusion bonding. So you put 2 metals into contact at high temperature with some pressure, and then some diffusion is taking place. The atoms are mixing in a very small zone, and this gives a stable bond of these two alloys. And we are doing just the same, and this is an example that we did on copper alloys. So you see these samples in the top image. There are 4 or 5 rings, and you can see from the color that these rings have different composition. And in the lower image, you see the cross section. So you see the 4 rings, and in the center there is a cylinder, and these rings and the cylinder are bonded together by diffusion bonding, and then so that they're in intimate contact, and so that diffusion can take place. And by diffusion, the compositions of these different alloys are mixing. So in this diffusion zone, which is maybe 1 millimeter wide, we get a mixture of all the 3 alloys in this case at the contact point, and we get hundreds of compositions within a very small range. Now we have to measure these compositions, and we can do this in the electron microscope and by microhardness measurement. And this is what we've done here. So you see the 3 different alloys from this example. You can see them here in 3 corners of this image. And the points that you're seeing here are hardness indents. And you can already see by eye that in some regions the hardness indents are larger. This means the alloy is softer, and in some regions they're smaller, so the alloys there are harder. Now we have to match the composition of the alloys with their hardness. And there are these 2 triangle diagrams. The left one is showing the hardness as a function of composition in the annealed condition. And the blue colors indicate that all the alloys are quite soft. Now in the right diagram, you can see that there are areas in red and yellow color. And this diagram was measured on the same sample, but after the sample has been annealed at 450 degrees for some hours. And then the so-called H-hardening process is taking place. And we see that there are compositions that show high hardness, while others still are staying soft. So with this method, we can screen a whole composition range and find alloys that have the potential for H-hardening. With all these samples that are shown here, we have thousands of compositions that we can screen with a few samples. We can also get more information from these diffusion couples. So this diagram here, or pictures here, are showing on the upper left side the diffusion couple. So the 3 copper alloys, you can identify them from the different colors. And now just from the image, I can extract the color values, LA, B, and C, LA and B value. So I can match the composition with the color. I can also match the composition with the color after a corrosion test. I can do scratch testing. I can measure the electric conductivity. So there is much more than just looking for hardness. With such screening methods, we have a powerful technique to experimentally screen whole alloying systems. Another technique, this is a very old example I found from Jörg Fischer-Bühner's work. This is done, there is a diagram missing here. This was obtained by sputtering technique. So the picture here is showing a glass plate, maybe like 20 times 20 centimeter. And then we used sputtering technique to deposit alloying elements on this glass plate. And we used 3 different alloying elements: aluminium, indium, and gold. So they are arranged in a triangle. And so they're sputtering material from different sides. So we get mixtures of alloying elements on this glass plate. And now we can anneal this glass plate, and we find the blue and the purple color forming. So the lower image is in the annealed condition. And this also helps us to screen interesting composition ranges. And now we can use different mixtures of sputtering targets to determine the resulting color. But of course, we can also measure other properties like the hardness, electric conductivity, and so quite similar to the diffusion couple. But there are two there's a difference between these two methods. With the sputtering technique, we map the area over a wide range, which makes it easy to characterize the properties. With the diffusion couple, everything is in a very narrow range, so we have to have very specific measurement techniques. So that's a benefit of the thin film coating. On the other hand, the thin films are just thin films, so they might behave different than a bulk material. And so with the diffusion samples, we are much closer to the bulk material. So ideally, we can use a combination of these two different techniques. Okay. Now, to finalize, the digitalization in material science is a trend at the moment. And you probably have heard about a digital twin or about ontologies. And so what does this mean? We have data from many different processes, from the casting processes, from computer tomography, tensile tests, from metallographic images, hardness measurements, and so on. And also from simulation techniques. Now, all these different results are related, but they are, the data are generated in different systems. And they are located on different computers, maybe on different network drives, and maybe you don't know where all these data are. And after half a year, you don't know maybe how you measure them. So you not only need the data, but you also need the metadata, the information about how your data were generated. And you have to link all these information. Now you can make big Excel sheets, and after 3 months, you forgot how you arranged the Excel sheet. So what is done is a so-called ontology is developed. An ontology is describing all these links. It's like a language. It says there is a machine that has an oven with a temperature that has 800 degrees and a time for 1 hour. And there is a sample that goes through this oven, this heat treatment process, and the sample has certain characteristics and has identifiers. And all this information is linked together. And so this is more than just a database. It also contains the link between the different processes. And this allows you an in-depth data analysis, much more than just sitting there and collecting your data and putting on paper. And you can find more complex relationships between the materials and the processes. This is something that is currently built up in pilot projects, and there are programs especially in Germany, but also in the European Union and many in the US that are looking for such development of such digital twins. And I think the jewelry industry, I'm not aware about projects in the jewelry on this topic. So I think this is something that is very interesting also to follow the process change for and for the complete description, not only of the material or the process, but the complete description of the system. So with this, I would like to summarize. I showed you that alloy development is a complex work. There is a a sheer number of alloying elements makes it very difficult to do all the work experimentally, so we have to use screening approaches based on simulation or experiments, or ideally a combination of both. And in the future, we should look for the development of such digital twins that allows us to describe the whole environment of production and use of our alloys. So, thank you very much.